Bayesian tracking of video graphs using joint Kalman-smoothing and registration. Graph-based representations in videos provide a convenient setting to represent and analyze higher-level structures of scenes in video sequences. We can represent the detected objects as nodes and their interactions as edges in a graph. As the objects and their interactions change over time, one obtains a time series of graphs representing an evolving scene. The node attributes are often descriptive of objects and their spatiotemporal locations in the scenes. The edge attributes are designed to capture pairwise relational properties of objects. However, computer vision-based object detections in scenes have limitations such as noisy, cluttered, and misdetections. A misdetection occurs when a subject is present in the scene but is undetected by the object detector. False or noisy detections occur when there is no subject in the scene and yet something is detected, or when a subject in the scene is detected multiple times. Graphs can have random ordering of nodes without altering the scene descriptions, although it may change the mathematical representation. Previous graph-based methods typically assume graphs with fully registered nodes and do not account for clutter or missing nodes. Furthermore, we note that the classical Euclidean filtering techniques do not apply directly to this non-Euclidean space of graphs. Our work adapts a Kalman filtering and smoothing approach to the non-Euclidean geometry of graphs to perform Bayesian inference. We formulate an inference in the quotient space of graphs modulo the node registration group. Incorporating registration allows for optimal matching and tracking of nodes over time and handles the presence of missed and false nodes from noisy observations. We introduce a novel framework for Bayesian estimation and tracking using Kalman filtering and smoothing for time series of graphs. A graph formulation provides joint inferences on the detected objects and their interrelationships. We first evaluate our method on a series of simulated graphs, imitating the complexities in real data, such as missed and spurious detections in the observed series. The temporal registration process can add null nodes with 0 degree, thereby retrieving undetected nodes. We see a near perfect estimation of the system graphs. We finally consider the model's performance on the bus station scene in the MEWA dataset. We consider video clips showing an event of interest, such as a subject entering the bus station, walking across the room, or taking a seat. The performance is compared with several models: multi-epoch training, online training, and static or reactive prediction models. The estimation errors indicate consistently high prediction accuracy for Kalman-smoother. A key advantage of our framework is the elimination of noisy and retrieval of misdetections. Some cases of success as well as failure are shown here. In summary, we develop a Kalman-smoother approach adapted to the quotient space geometry of graph representations to track objects of interest in video data. The Bayesian framework helps overcome the issues raised by missed and false detections in the pre-processing step. Our model outperforms several learning-based and some online ideas. Thank you.